Okay, welcome to the lecture here. We're continuing on in chapter 10, and we'll get started here in just a second. Okay, so last time we were talking about chapter 10 and a little bit about solutions. Before that, obviously, I think that most of you probably hopefully saw the announcement. The exam will be moved to Monday, and it will cover this chapter and obviously the previous chapter and a little bit of that gas chapter that we didn't get tested on. There wasn't very much left of that, but that will be what will happen. So just to give everybody a little bit more time, since this chapter is going to be on there and we kind of just started getting into this topic here at the end of last time. Not the best situation, but I guess it'd be better than maybe having it tomorrow on the stuff we're talking about today. So we're going to do it on Monday. We'll take the exam, and then obviously on Thursday, that's it. We have the final afterwards. So that stuff will be on the final as well. So as you're studying for that, that should hopefully take care of 2 to 2.5 chapters for the final in terms of studying. So that stuff should still obviously be fresh for you. So that's the plan. So tomorrow we'll have a normal day. We'll have lecture, and then we'll have lab and all that like normal tomorrow. And again, on Monday, we'll take the exam like we've been doing right around lab time is when we'll take it. So we'll have a short lecture on Monday like normal, and then have the exam there on Monday. Okay. All right. So we just got into sort of this chapter, or made some progress into this chapter here about solutions, and some of it we did cover a little bit of some of this stuff earlier as well in some other chapters, and it's in this chapter as well. But we started talking about solutions and the idea of sort of solubility and the idea of like dissolves like. So remember that when we're dealing with solutions, or really sort of any substances, but solutions in general as well, there's that idea of like dissolves like, which means basically things that have very similar intermolecular forces interact well with each other. So they're typically soluble in each other. So again, things that are using sort of dipole-dipole and dipole-dipole, maybe dispersion forces and dispersion forces are very soluble in each other. So things that are typically polar and polar will mix really well. If things are nonpolar and nonpolar, they also will mix. Things that are ionic and polar will mix as well. And again, they use sort of that ion dipole interaction we talked about with intermolecular forces. And this allows them to basically mix well. And if we're talking about sort of a solid in a liquid, we talk about it in terms of solubility. Something is being soluble in each other. If we're talking about sort of two liquids mixing, it means that they are insoluble, they're miscible in each other. If two things are not soluble in each other, then they are insoluble. And if two solutions, for example, do not mix, they are immiscible in each other. So you'll see different layers that basically occur. Excuse me for 1 second here. Okay, sorry about that. So as I was saying, if we have sort of two solutions that really do not mix in each other, again, you'll see these sort of layering that will happen, and especially in like liquids in a test tube, and they definitely won't mix. And again, that's really because they're trying to use different types of intermolecular forces, and they can't, for the long period of time, be able to basically interact with each other. Again, that's why, you know, everything sort of mixes together for a little bit, but there's things that over the long period of time can't maintain that mixing, and they will sort of separate apart from each other. And again, for example, we talked about oil and water. Again, typically there'll be two different layers. The oil trapped on top of the water or traveling on top of the water there. Again, because they have no really long way to maintain that connection. We also sort of reviewed some concentration type units that we saw earlier that's officially in this chapter, I believe. And, you know, those are things like obviously molarity, which we should be familiar with. Also things like molality, which is little m, which is our moles of solute per kilogram of solvent. Also our percent concentrations like mass to mass, right, which is our mass of our solute, mass of the solution, times 100%. With that, we also had mass to volume that we talked about, volume to volume, which works very similar, mass of solute over volume of solution, volume of solute over volume of solution. We also saw, again, our mole fraction, right, which is, again, the moles of what you're interested in divided by the total moles. And these are some important sort of concentration units that we touched upon earlier on in this semester, which again are obviously in this chapter. And two that we've sort of seen here towards the end of this chapter that's really sort of important that does pop back up is these two here. The molality is used and the mole fractions used in sort of the topic that we sort of finished on yesterday, which was colligative properties. And colligative properties of solutions are the properties of solutions that are dependent on the number of particles that are dissolved in a solution. And the number of particles that are dissolved in a solution is important because they essentially, for the lack of a better sort of analogy, get in the way of sort of the natural process that occurs when something, say, like water would want to freeze or boil. So as we talked about yesterday, if you have just plain old water by itself, if it wanted to freeze, if it wanted to basically boil and evaporate, if it's in there by itself, it essentially has nothing in its way. So it either could, all the waters can come together sort of unimpeded by anything else in there. If the waters need to break apart, they can break apart and get to the surface relatively easy. Again, there's nothing really but water molecules present. But that does sort of change when we dissolve something in a solvent like water, and it doesn't always have to be water, but it could be something similar to water, another type of solid. But when we do dissolve sort of things in there, you know, whatever it may be, sodium chloride, any other type of ionic compound, now what you have are these other particles that sort of, if you want to think about it this way, get in the way of sort of the natural coming together, for example, of water when it would freeze. Also, its boiling aspect is it gets in the way as they try to travel out of the solution. And this results in changing some of those properties that we associate with the solvent by itself. So, for example, water normally freezes at 0 degrees Celsius. If you dissolve some stuff in it, in water, the freezing point will lower. So again, instead of maybe 0 degrees Celsius, maybe it freezes at, like the first example we did, our last example we did last time, like -3 degrees or something like that. Same thing with the boiling. Normally boils at 100 degrees, but since these particles got to kind of work their way around all these other floating particles, these water molecules, they need a little bit more energy to get themselves around there and stuff. So instead of boiling at 100 degrees Celsius, it takes a little bit more energy to get them free and into the gas phase. So maybe it boils at like 105 or 102 or something of that nature. So we saw some formulas that involved sort of other aspects that are affected as well. And the other one that we talked about as well was the vapor pressure and the vapor pressure lowering. And again, the vapor pressure is that pressure above the liquid. It's a result of gas molecules being present. Obviously, that's what causes the pressure. So when we do dissolve things into a solution, again, it's going to take longer, just like the boiling point, longer for those guys to escape the solution. So we're going to have less gas molecules above the solution part. And because we'll have less gas molecules above the liquid part, the vapor pressure will go down because, again, there's less gas molecules in that sense. So that's what's known as vapor pressure lowering. And we saw sort of an equation, which again, for vapor pressure lowering, uses that mole fraction that we talked about. Again, this is the vapor pressure in the solution. This is the vapor pressure of just the pure solvent by itself. And this is our mole fraction. Those are supposed to be Z's, not 2's, by the way. Bad looking Z's. So again, here we did an example of that, and we saw sort of in the pure solvent, the vapor pressure was like 63, I think. And in the sort of one where it had the glucose dissolved in it, the vapor pressure went down to like 57 or something like that. So again, it's lower and affected by the number of particles that are present. We also saw some formulas that relate to freezing point and boiling point, and those were the delta T of freezing equals Kf times M. And this is the change in freezing point temperature. So not the actual freezing point temperature, but that is the change between where the solvent would normally freeze to where it freezes in the solution. Kf is a constant, which is on this table here. And that's what is sometimes referred to as the freezing point constant. And it is dependent, again, here on the solvent, not the solution. So very often people are like, I can't find the Kf because they're looking for, say, something like sodium chloride or something like that. Again, here, you want to look for the solvent on this list. And the solvent, for example, could be water, which means you would want to use this equation here. We also saw one for boiling, which is the pretty identical equation here. Delta TB equals KB times M. Same thing, the little m is the molality on each side. So that little m in that formula is the molality. And the KB here is our boiling point constant, which again also can be found on the table. Also dependent only on the solvent that's present. Now, when we do sort of the change in temperature part, it's important to remember sort of what that means for each of these, and it's slightly different. When we do the change in temperature for freezing, because it's a freezing point depression, we take the temperature of the solvent where it normally would freeze minus the temperature of the solution. And again, that one is important because that will give us the correct sign. So the last example that we did, if you remember, we got a change in freezing point of about 3 degrees, but using this correct arrangement basically gave us that negative sign that we ended up with in terms of the actual freezing point temperature. And that's different than our boiling point because it's boiling point elevation. So when we do the change in the boiling point, we actually do the opposite. We take the temperature of the solution that has the stuff dissolved in it, minus the boiling point temperature of just the solvent by itself. This also will give us the correct sign. It will also, more importantly, probably for the boiling point, give you the correct should I subtract or add, to that. And again, you can just remember it by elevation, so probably should go higher. Depression should go lower than where the solvent normally starts at. But those two sort of formulas helps us sort of get the right sign, get the right adding or subtracting. Any questions on any of that stuff there? Okay, so this was the example that we did last time, I think. So I think we are here. And we're looking for, in this particular example here, the molar mass. So let's go through this one here, I think, together. And then I think you'll have some examples to do next. So let's see how we get through this one. So here we're looking for a little bit something different. We're looking for the molar mass of a compound that is made up by dissolving 12 grams of it in 80 grams of water, and it freezes at minus 1.94 degrees Celsius. So we're looking for a couple of things here. We're obviously looking for molar mass, so we are looking for, we'll get some numbers there that will help us. There we go. We're looking for molar mass, so the units of molar mass is grams per mole. So we're essentially looking for both of those things. And the one thing that we do have right off the bat is the grams. So we took 12 grams of this guy, and that means that we have the grams ready to go. So we don't have to do much with that other than obviously put it into here. So what's left to find is the moles part, and the moles part is going to come from the other information that's there. And we got that the water freezes, I'm sorry, the solution freezes at minus 1.94. So since it's freezing, we do want to use our freezing point equation. So the change in temperature of freezing is equal to our Kf times our molality. And we do have a couple things. We do have what the temperature of it freezing is. And we do have the Kf, which is a constant. So we can look at this. And we can have this. So what this is going to leave us in terms of this that we really don't have is the molality. So we could actually use this to solve for the molality. But a very important note here is that that is the temperature at where the solution freezes, which is minus 1.94 degrees Celsius. And this is where using that relationship for this is important, because this number is actually not the change in temperature of freezing. So if we do our change in temperature of freezing, as we talked about, is the temperature of the solvent minus the temperature of the solution. So the solvent, I'm sorry, so the, what we got here, the solvent is 0, where it normally freezes, minus our minus 1.94 degrees Celsius, which is where the solution freezes, gives us a positive 1.94 degrees Celsius. So that is how we get it to a positive number, is by putting it into that relationship there. It makes a difference because ultimately we can't end up with a negative number here. So that's what the 1.94, that's how we essentially get rid of the negative, by putting it into this relationship here. So now if we solve for M would equal the change in the freezing point temperature divided by Kf. That would be, again, our positive 1.94 degrees Celsius. Kf, which is a constant that you could get for the table, here looked up for water, which is our solvent, and that is 1.86 degrees Celsius divided by the molality. And if we do that, we get 1.94 divided by 1.86. We get 1.04 as our molality. So remember, though, that we are trying to find the moles, and that little m is not moles, that is the molality. So also a reminder that the molality, as we just saw and talked about before, is the moles per kilogram of solvent. So if you think about the numbers we've used this number, we've used this number. The only number we got left is our 80 grams of water, and water is the solvent here. So now that I have the molality, I could take that as moles per kilogram of solvent. And if I take my 80 grams, I do need to convert it to kilograms so that the units cancel. So 80 grams, 1,000 grams in a kilogram gives you something like 0.08 kilograms. So if I multiply this by 0.0800 kilograms, kilograms are going to cancel, and I end up with 0.08344. And that is this number here that I need, which is our moles part. So now that we use basically the freezing point information to figure out the moles, and we have the grams, what's left to do is simply divide the two numbers and see what we end up with. And if I could get some stuff out of the way here. There we go. There we go. So the molar mass in this case would be our grams, which was given to us, or 12 grams, divided by the moles we just calculated, a 0.08344 moles. And if we do that, 12 divided by our moles gives us 143.8, or we'll call it 144. 144. Units don't cancel, so grams per mole. So here we can use our freezing point information to allow us to find something like moles, and the grams that is given to us to find something like the molar mass of a particular substance, just based on how it freezes, how it boils as well. Question on any of those steps there. And again, it's important to get rid of that negative sign like I did there for the 1.94. Otherwise, obviously, as you can see, if you did not do that, you would end up with a negative molar mass, which shouldn't happen. The good news is you'd have the same number, and if you realize that, you could get rid of the negative at the end, but you would have obviously the wrong number if you put the negative there. Any questions on that? All right, so now that I've tried one or two here, why don't you try some? So why don't you try the next one and see what you come up with. Here we're looking for how many grams of ethylene glycol must be added to 1 kilogram of water to give a solution that boils at 105 degrees Celsius. And I want to give you some information that will be helpful for you. Molar mass here of carbon, right, is 12.01. Hydrogen is 1.008. Oxygen is 16. And here we're doing boiling, and it's involving water. So we do want to look up the KB. And again, here the KB would be for water, and the KB value for water is 0.512 degrees Celsius divided by molality. So take a couple of minutes to see what you come up with. We're looking for how many grams basically the antifreeze needs to be added to 1 kilogram of water to give a solution that will boil at 105 degrees Celsius. So see what you come up with. Okay, so let's take a look at this one. So we want to know how many grams of ethylene glycol must be added to a kilogram of water to give a solution that boils at 105 degrees Celsius. So some of the key points here is obviously we're talking about boiling. So we do want to use our boiling point equation here. So our delta TB equals our KB times our M. Again, our KB here is related to the solvent, which is water. So we know that this is our solvent. And that is that value, obviously, you could get from the table. So we do have the KB value given to us. We do have a solution that will boil at 105 degrees Celsius. So we do have some information to get to this guy. So just like the last one, the piece of information we're sort of missing here is the molality, which is moles per kilogram of solvent. And that's going to allow us to eventually get to the grams of the solute, which is basically this guy, right? The ethylene glycol is the stuff dissolved. It's the solute in the solution. Just like before, though, the temperature that they gave us is actually not the change in the boiling point temperature. It is actually the temperature at which the solution boils. So we do have to use, again, that relationship here about the change in the boiling point temperature. So this is actually going to be the temperature of the solution where it boils minus the temperature of the solvent where it normally would boil. So in this particular case, they told us that it boiled at 105 degrees Celsius. The normal boiling point of water, which is the solvent by itself, is 100 degrees Celsius, which means our change in boiling point temperature is really just 5 degrees Celsius here. So that's an important distinction here. You don't want to go in again with the 105 because, again, that is where the solution boils, not the change in the boiling point temperature. Again, the change, as you can see, is basically it's going to boil 5 degrees higher than the solvent by itself. So now that we have sort of the right numbers here, we could solve for M, which would be our change in boiling point temperature divided by our KB. That's going to give us 5 degrees Celsius divided by the KB that we looked up there on the table. And if we do that, we will get 5 divided by 0.512, 9.77 little m, which again means that we have 9.77 moles of solute per kilogram of solvent. So ultimately, we're looking for the grams of our solute. So we do need to get rid of the kilogram part here. So that's pretty easy. They told us that our solvent was 1 kilogram. So if we just simply take this times the 1 kilogram of solvent, the kilograms will cancel. And the good news is, since that's 1, this is also still going to be 9.77 moles of our solute, which in this case is the C2H, what we got there, 5, I think, right? O2. So what's left to do at this point is to convert the moles into grams. So that's why we have our molar mass information up here. And if we figure out the molar mass from the periodic table, we got 2 times 12.01 plus 5 times 1.008 plus 2 times 16 gets us a molar mass of about, unless I'm getting old, but that's 6. It is a 6. That would be a better number there, huh? So that's why it doesn't seem right. It's actually a 6. So we'll add 1 more hydrogen to it. Gets us 6207 as the molar mass. And if we take that times our 9.77, gets us something like 606 grams of this guy is needed. And I suppose if we do a little bit of cleanup here, probably something like 610 grams on some significant figures. based off of back this way, the two that are there. Question on that calculation there. So basically, if we take 610 grams or so of this and we put it in basically 1,000 grams of water, give it a nice mix and shaky, it should all start to boil at not 100 degrees Celsius, but it will boil hopefully at 105 degrees Celsius. Any questions on any of the part of that calculation there? If you're asking how do we get 610 in terms of rounding to that number, I'm assuming is probably the question. If that's the question, then the rounding to the 610 was because significant figure wise, we did this calculation here that I kind of ran over the number there, but it basically was 1 kilogram. So that's 2 sig figs right there. And if you carry that over to here, technically speaking, this answer should be 2 sig figs. And then obviously when you multiply it here, it should end up back to about 2 sig figs or so when you did that. Other questions on that? Okay. So why don't you try another one here and see what you end up with. All right, so why don't you try this one. Calculate the boiling point of a solution that's made by dissolving 1 gram of glycerin in 54 grams of water. And a couple of pieces of information, probably the same numbers you can use from the last one. We're still using boiling here, right? So still the same KB because it's water, 0.512. And obviously still the same boiling point temp of 100 degrees Celsius for our water. And then obviously the same numbers there as we had before, carbon 12.01, hydrogen 1.008, and oxygen 16. All right, so see what you come up with. Here we're actually looking for what is the boiling point temperature of the solution that has this glycerin basically dissolved inside. Take a couple minutes, see what you come up with. Okay, so let's take a look and see how we're doing. So here we're actually looking for the boiling point temperature. So obviously that gives us some information. We want to use our boiling point formula here. Excuse me. Kb times the molality. And that means we need to figure out some things here. We have our glycerin, which is our solute. And we have our water, which is our solvent. Again, we know that definition of the solute, right, is the smaller part of the solution. Larger part is the solvent. So water, usually a pretty good solvent. A reminder that it's not always going to be water. So although these few examples here have been water, it can be something else other than water. And you want to make sure, as we talked about last time, that if it's not water, whatever the sort of solvent is, you obviously get the right Kb or Kf value, and then you also use the correct boiling point or freezing point for that particular solvent. So remember, when we talk about 100 degrees and 0 degrees, that is specific for water. And I think it's specific for water and not, some other substance. So in this particular case here, we have the grams of our solute, we have the kilograms of our solvent. That is going to allow us to get to molality here, and the Kb we have. So that would be probably the first thing that we want to do, is figure out the moles of our glycerin. And we will use the molar mass there of glycerin. And if we go to the periodic table and look up the molar mass or calculate it from the formula, the molar mass of it looks like it comes to something like 92.09 grams per mole. So to figure out our moles of glycerin, we're going to take our 1 gram of our glycerin, which is our C3H8O6. We're going to divide it by our 92.09 grams per mole. And that's going to give us our moles of our solute, which looks like it will be 0.01086 moles. Here we're then going to divide it, right, to get to the molality, which is our moles of solute, kilograms of solvent. So that would be the top part. The kilograms of solvent going to come from our 54 grams of water, which is 54 grams, 1,000 grams in a kilogram, right? Basically just going to move the decimal place a few places to the left there, giving us 0.054 kilograms. So now that we have our moles and our kilograms, we could get our molality, which would be 0.01086 moles divided by 0.054 kilograms. That gets us 0.201 for our molality, which again is the one piece of information that we need. The Kb is a constant. So now we have both of those pieces of information, and that will give us the change in boiling point temperature of our Kb, which is 0.512 from a table is where we get that. The molality that we just calculated. The two m's cancel and leaves us with degrees Celsius. And that gives us something like 0.103. So that's 0.1003 degrees Celsius. Now, the important part here is, again, this is not the answer in this case. This is just the change in the boiling point temperature. We're looking for the actual temperature at which this solution would boil. So again, this is where that relationship's important. Change in boiling point temperature is the temperature of the solution minus the temperature of the solvent. Again, the solvent, which is water, normally boils at 100 degrees Celsius. So the important part here is we will end up with 0.103 degrees Celsius equals the temperature of the solution minus 100 degrees Celsius. This is important because now we're going to add it to this side, right? And when we add it to that side, we end up with something like 100.1 degrees Celsius will be the temperature at which the solution should boil. Not a giant jump in the boiling point, but still went up by about 0.1 of a degree because of this glycerin that was basically dissolved in the solution. Question on any of those steps there? So again, as I mentioned earlier, this relationship here for our boiling point is really important. And the one that we have for the freezing point, that's a similar one, just sort of reversed, is also important because again here, if you had it opposite, you may be subtracting when you should have been adding. And again, you want to make sure that you sort of get the correct answer. So a couple of places where people do sort of go bad on that is this part. They think this is the answer for the boiling point temperature. And B, they don't get the right sort of relationship here. And again, like I said, they sort of add when they should subtract or subtract when they should add. So you want to make sure you just watch out for those kind of things. Question on freezing point or boiling point or any of that stuff there. Okay. So the next sort of property of a solution that's important is what is known basically as osmotic pressure. So osmotic pressure is basically if we have, say, two sort of solutions that are a solution that's separated by a membrane. And a semi-permeable membrane allows certain size molecules basically to pass through. Other size molecules can't really get through because of sort of the holes, if you will. The size, they're too big basically to fit through the holes of the membrane and kind of go through and stuff like that. So we'll see maybe a better picture of this in a little bit here, but say you had in a sort of container or a tube that has a membrane sort of in the middle. And on one side, you had just sort of pure water. And on the other side, you had some salt water. And what will happen is through the process of osmosis, which is basically the solvent water molecules will travel from an area of lower concentration to an area of higher concentration. So salt being in the water on the right-hand side of the membrane is more concentrated than just pure water. And what will happen is the water will flow across the membrane in an effort to really sort of dilute down the salt water on the other side, which is more concentrated. And it will continue to flow basically through this osmosis until it reaches basically it's hit by an opposite pressure, which is known as the osmotic pressure. And that's a pressure equal to, or maybe equal to the atmospheric pressure, basically pushing back down on it. And what happens is it will basically stop the water from flowing from one side to the next. And that's basically what's known as the osmotic pressure. It stops that flow of solvent molecules from one side to the next through a sort of membrane. And osmosis, as we'll talk about, is sort of a natural process where things will flow from a lower concentration to sort of a higher concentration, again, in an effort to sort of dilute it. Osmotic pressure is based on the number of particles that are in there. The more particles, the greater the osmotic pressure and so forth. Water has no osmotic pressure, pure water, because it has nothing dissolved in it. So it basically has no osmotic pressure associated with it. We could actually calculate the osmotic pressure by using this formula on the bottom. So this little pi sort of symbol represents the osmotic pressure. And really, if you look at this, this should look very familiar to you. This is really the ideal gas law, PV equals nRT, just with a different symbol for P. Instead of just calling it generically P for pressure, they use this little symbol, almost like a pi symbol, for osmotic pressure. But it really is, as you can see here, if you divide V to the other side, it's really P is equal to nRT divided by V. It's the exact same thing that's here. Also, a relationship that we talked about is the N over V part, right? As we talked about with the N over V part, N is moles, right? And V is liters. So that together becomes molarity, which is what the big M is here, right? And if you kind of simplify it, the osmotic pressure is equal to the molarity times R times T. T, just like normal, since it is the ideal gas law, does need to be in Kelvin. And R is the gas constant that we use for the ideal gas law, which is this value here. So the good news about sort of osmotic pressure is it essentially is, the ideal gas law. And, so again, that's something that you've seen before and should know how to sort of deal with it. And again, a reminder that because it really is the ideal gas law, you do want to watch units. You want to make sure everybody's in the correct units when you go into there. So let's take a look at a guy here. What is the molar mass of a protein that is 5.87 milligrams per 10 milliliters, gives an osmotic pressure of 2.54 torr and 25 degrees Celsius. So a couple of things we're looking for here. We're looking for grams per mole, which is our molar mass. And if you think about the grams part, we essentially have it here. It is in milligrams, but we do need to convert it to grams, and then we can go into here. So kind of like the other molar mass problem, we're missing the moles. And we can see that we have a pressure, we have a temperature, and we do have a volume. So again, that's a lot of the information that you need for really the ideal gas law, which is again your PV equals nRT. So again, we have the pressure, we have the volume, we have the temperature, and we always have R. So you can see that the only thing that we really don't have here from the ideal gas law is N, which is moles, which is good because that is exactly what we need. So here we're just going to really do it like an ideal gas law problem. We're going to solve for N. N would be PV divided by RT. And as I mentioned before, even though it's sort of wrapped up as osmotic pressure, it is still really just the ideal gas law. So we do need to do some conversions. We know, right, when we go in there, the pressure does need to be in atmospheres. So we got to convert that to atmospheres. So we need to take our 2.45 torr divided by 760 to get it into atmospheres. And if we do that, we end up with 2.45 divided by 760 gives us an atmosphere of 0.00322 atmospheres. We also need to convert our temperature into Kelvin. So that's a 25 plus a 273 gives us a 298 Kelvin. And our volume, right, does need to be in liters. So we need to take our 10 milliliters divided by 1,000. And that gets us 0.01. Go here, 0.01 liters. So now we got everybody converted into the right units. We're going to put it in here. So again, our pressure was 0.00322 atmospheres. Our volume 0.01 liters. Our R, which is the same R we've used before. And our temperature in Kelvin. Again, much like what we've used before there, everything's going to cancel out except for moles here, which is good because that's actually what we're looking for. So we'll take some of these numbers here. Take that times 0.01 divided by 0.08206 and divided by a 298 gets us a very small number here. So we'll go scientific notation because I don't want to write all the zeros. 1 point, we'll call it 32 times 10 to the minus 6 moles. So a lot of zeros there. So now that we just did that, we now have our moles part. We do have to convert our milligrams into grams. So 5.87 milligrams, 1,000 milligrams in a gram. That gets us 5.87 times 10 to the minus 3 grams. So now I finally have everybody in the right unit. So my molar mass will be my grams, 5.87 times 10 to the minus 3 grams divided by my moles. And if we do that, we end up with a molar mass of 4.45 times 10 to the 3 grams per mole. So that's about 4,400 grams per mole. That's a big number, but it is a protein, so it's got a lot of stuff going on there. So we would expect a larger molar mass on that. Question on any of those steps. So kind of similar to what we did, we're kind of using the osmotic pressure here to really figure out the molar mass. It's really very similar to, if not identical almost to, when we talked about calculating the molar mass of a gas, basically. It's the exact same sort of calculation. Any questions on that there? Okay, so you got one there. Why don't you give it a try and see what you come up with? So here you want to look for the what is the molar mass of this lysozyme. That's 0.075 grams per 100 milliliters and gives an osmotic pressure of 1.32 times 10 to the minus 3 atmospheres at 25 degrees Celsius. So see what you come up with. Okay, so let's take a look. So again, kind of like the last one, we are looking for the molar mass, which is grams per mole. And out of that, right out of the question, we do have the grams part here. So that's the top part, which in most cases in these type of molar mass type problems, usually are given the grams somewhere in the problem or an ability to get to the grams in most cases. If we think about what's going on here, we have osmotic pressure. So really you can kind of think about the ideal gas law when that is sort of mentioned. And we do have a pressure given to us, just like before. We have a temperature and we do have a volume here. So just like last time, we have enough information to figure out the moles part using really the gas information. So we do have to do a couple of conversions here. Again, our temperature, we need to add 273 to it to convert it to Kelvin. And our milliliters here divided by 1,000 will get us to 0.1 liters by dividing it by 1,000. And in this case, our pressure is actually in the right units. So just like last time, we could solve for N, which would be PV over RT. Our pressure there being 1.3. 2 times 10 to the minus 3 atmospheres. Our volume, which was converted to liters, 0.1 liters, divided by our R, and our temperature at 298 Kelvin. So if we do all that there, we got 1.32 exponent minus 3 times 0.1 divided by 0.08206 and a 298 dividing gets us a mole of 5.40 times 10 to the minus 6 moles, which again is the bottom part of what we were looking for there. And in this particular case, we already had the grams. So our molar mass in this case would be the grams from the problem, divided by the moles, which is basically your definition of molar mass. And that will get you we'll call it 39 times 10 to the 4th grams per mole. Again, both of these are proteins and we'd expect a larger molar mass in terms of the number here. Question on any part of that calculation or osmotic pressure, which again, like I said, it's essentially the same calculation a lot of times as either using the ideal gas law or like what we did here, using it to figure out the molar mass of something, which is also something we talked about in the gas chapter. Any questions on osmotic pressure? So again, the osmotic pressure is basically the sort of pressure required to stop the flow of solvent molecules through osmosis. All right, the next thing we're going to talk about then is a little sort of tweak on some of the formulas that we just talked about here in terms of vapor pressure lowering, boiling point elevation, freezing point depression. So if you've noticed in all these examples that we sort of talked about up until this point, or maybe not, but when we pointed out to you, when we looked at the solute in all of these sort of examples that we used here in all these sort of problems, they were all molecular compounds. So if you think about the ethylene glycol, so let me come back to, not this stuff here. Here we had, C3H8O3. The other one was like C3H6O2 or something like that. They were all basically molecular sort of compounds. And if you remember, the idea here behind sort of colligative properties, which is what we're talking about here, is they are affected based on the number of particles that are in a solution. Now, when we're dealing with something that's non-ionic, it's sometimes referred to or being molecular, they stay together, right? They're not ions, so they're molecular, they're all bonded. So again, if you take like glucose or sugar, when that goes into solution, it all stays together as like one whole sort of molecule, which means it's sort of a one-to-one relationship in terms of what's happening in the number of particles that are being made. Now, if you take something that's ionic, say like sodium chloride, and you drop it in there, you get a sodium ion and a chloride ion. That is 2 ions that are formed for every one of these guys. And again, that's going to affect those properties because now you have twice as many ions that would be floating, particles that would be floating around. That's something like calcium chloride, for example. It would break apart into a calcium ion and 2 chloride ions. You get like a 3-to-1 sort of ratio there, which means you're going to have 3 times as many particles floating around if you dissolve calcium chloride in water than, say, glucose in water. And this sort of factor does affect, you know, what happens in terms of things like boiling point, freezing point. And we use what is known as the von Hoff factor. And that von Hoff factor basically is a correction value for how many particles are coming into that solution. Now, when we look at something like glucose, it's essentially 1, right? And we look at something like sodium chloride, I is equal to 2. So the von Hoff factor is sometimes used as I, and I is basically equal to the number of particles that are present. So I for, say, glucose would be 1, I for sodium chloride would be 2, I for calcium chloride would be 3. Now, how does that affect those formulas? So basically, we use the exact same formulas. The only difference is we do insert that factor into there, that I factor, which is the von Hoff factor. And these are the 2 most common ones that you deal with it. You could also use it for vapor pressure lowering as well. You just basically insert the I. Everything else is done the exact same way, but you do have to sort of use it almost as a correction factor for the number of ions that are present. Now, most of the time, we'll just use I based off of the actual formula. So I would be 2 for something like sodium chloride, breaks apart. I would be 3 for something like calcium chloride. And as we talked about for glucose, right, I would be 1 for glucose, which is why we didn't have the I in there to begin with in all those examples, because I would equal 1, which basically gives you the formula we were using, which is basically just delta TF equals KF times M. So when you have something that breaks apart into ions, you just insert that into the formula. Again, everything else works the exact same way. So this is really for when you have ionic solutes. You should use I. Now, I expected from the formula, as you can see here in this column, actually measured slightly off of it. So you can see sodium chloride is not exactly 2, but like 1.9, pretty close. This is iron 3 chloride, which technically breaks apart into 4 ions, and measured value about 3.4. So in most calculations, you could just figure out I based off of the actual formula, and it should be perfectly fine. But in reality, it is slightly different than what you would expect in certain cases. So basically, for any of those sort of formulas, again, the vapor pressure lower is another one that you could just insert the I into the right-hand side of the formula to take into account that the solute that we're dissolving is ionic. So let's take a look at sort of an example of that, or sort of how we could figure out the von Hoff factor. What is the measured von Hoff factor if 0.05 molality calcium chloride has a freezing point of minus 0.2 degrees Celsius? So here you kind of can approach it the same way. We're talking about freezing point. So we do want to use our freezing point equation. But the important part here is when we look at our solute, which is right here, it's ionic, which means we do need to sort of figure out what I would be. So if we were going to use this to solve for something other than I, we're actually solving for I in this case, but if we were going to use this to solve for something other than I, we would expect I to be, in this case, as we saw in the previous slide, have a value of 3, right? So what we're going to see here is how close our predicted value will be to what it actually is. So oddly, in this one, we're actually solving for I in this case. So we do need to figure out a couple things. The KF here is going to be the 1.86 degrees Celsius per molality. We know that an ionic compound, the solvent most likely will be water. So that's how we know that, right? Ionic guys are most soluble in water, and that's essentially what the aqueous means there. It's a water environment. So again, that is how we know to look up the KF value for water. We also know that the normal freezing point for water is 0 degrees Celsius. So we have pretty much almost everything that we need. We do have the molality given to us. So again, an important aspect of this is the change in freezing point temperature. Going to be the temperature of the solvent minus the temperature of the solution. So here, solvent going to be 0 degrees Celsius minus our minus 0.27, which is where our solution freezes. And again, this step shouldn't be overlooked because this is how we're going to get rid of that negative. And we will end up with 0.27 degrees Celsius as actually our change in freezing point temperature. So the idea there is it normally freezes at 0. It comes down 0.27 degrees to minus 0.27 degrees is the actual freezing point of that solution. We now could rearrange this and solve for I. I in this case would equal the change in the freezing point temperature divided by the KF times M. And again, we have all those numbers. So 0.27 degrees Celsius divided by 1.86 degrees Celsius molality. And in this case, we don't have to calculate the molality as it was given to us. And again here, molality going to cancel, Celsius going to cancel. We're left with just a number, which is good because we're looking for I. And in this experimental case, it is calculated that I comes to a value of 2.9, which is very close to the predicted value you would expect for I based just on the formula. Any questions on that? So again, an important sort of tweak of those couple of equations that we talked about, especially the freezing point one and the boiling point one, is if the solute is ionic, you need to use the formula and figure out what I would equal and basically insert it into the equation. Again, if it's something that's molecular, something with carbons, hydrogen, and oxygens, you don't have to worry about that. But if it's ionic, you do have to have that sort of correction value, which is known as the von Hoff factor, which is basically tells you how many particles are present. Any questions on that there? Okay, so again, a reminder of that. Make sure if it's ionic, you insert that I value. And again, you can use the I value just directly from the formula in most calculations. It should be perfectly fine. All right. So we're going to finish up here talking about some properties of solutions. So some of these things we talked a little bit about just a second ago, but again, a semi-permeable membrane is basically a membrane. You can't really necessarily see it, but essentially, you know, it's got like holes-ish or size. And again, it allows certain molecules, which are small enough, obviously, to pass through. Things that are too large, you know, aren't going to be able to get through the hole and get to the other side. Kind of like cell membranes, right? They act as almost filters, right? Filter certain things out. Certain things can go through based on size and stuff like that. When we talk about things that are known as colloids, colloids are really much larger than solute particles in solutions. These are large molecules like proteins or groups of molecules or ions. They're homogeneous. So if you remember, homogeneous means everything looks the same throughout. They do not separate or settle out. They can pass through filters like filter paper, but they're too large to pass through, say, a membrane. There's also things that are known as suspensions. Suspensions are heterogeneous. So again, heterogeneous means you see different phases, different layers. They're non-uniform. and they're very different than solutions or colloids. They're often really large. You can see it with your naked eye, and they pretty much don't go through anything. They get trapped on filter paper. They don't go through membranes, for example. So, for example, if you had sand and water and you poured it through a filter paper, the sand would be the suspension, right? You could see the sand in a beaker of water, right, with your naked eye. You don't have to zoom in on it or anything like that. If you try to pour it through a piece of filter paper, it's not going to obviously go through. So here's kind of a much better picture of a membrane than my bad drawing, but essentially you see the same thing. Again, there's sort of channels, if you will, or holes in the membrane, again, going to allow certain size molecules like solvent molecules, small solute particles to basically pass through. As you can see, these guys are not having any sort of problem getting through. But if something really large, like in this area here, this guy, he's going to have a big trouble trying to pass through there, and it's going to sort of prevent him from passing through, you know, sort of based on size. And here's sort of a picture of what we're talking about: solutions, colloids, and suspensions. As you can see, solutions and colloids will go through a filter paper, but the suspension gets caught up on top. While in a dialysis sort of bag or a membrane, it allows only certain size guys to go through, like the solution can kind of pass through pretty easily, but it will block out perhaps something like colloids and suspensions from sort of exiting through it. Just some information about each of those. Again, you can look at it, but we talked about most of those, I think. Let's then talk about, again, the process of osmosis. We talked a little bit about it earlier when we talked about osmotic pressure, but really osmosis is that process where solvent molecules really go from a lower concentration to a higher concentration, just naturally kind of want to flow that way. And again, the idea there is just trying to maybe dilute down the higher concentration to bring it back down in terms of its concentration. As we talked about, again, it will continue to flow until it basically hits that osmotic pressure. And again, when we had that little tube and a better picture coming up, but again, that water molecules, as we talked about, will continue to flow this way until it basically hits osmotic pressure. And that will eventually stop all the solvent molecules or water molecules from moving from one side to the next. Now, the greater the number of molecules that are dissolved in a solution, the greater the osmotic pressure. Again, the more molecules that are dissolved, the higher the concentration is, thus the higher the osmotic pressure would be. Now, pure water has no osmotic pressure, as we talked about, because pure water is just H2O, so it doesn't have any particles dissolved in it and has an osmotic pressure of 0. Also, reverse osmosis basically is the process where, you know, you apply a pressure that's greater than the osmotic pressure coming down this way. Make a giant arrow. And basically what that'll do is push all the water molecules back the other way. And if you have a pretty good filter right there as a membrane, it's going to filter out all the stuff you don't want in there, all the solute particles and stuff. And it will kind of sort of purify the water, if you will, by kind of forcing the water back in the other direction. And here's sort of a picture of that there. Again, a brine solution, that's basically like a salt solution. And again, because it also has salt in it, it is more concentrated. Pure water on this side, again, going to travel from lower concentration to higher in an effort to sort of dilute it down. Again, it will stop once it hits that osmotic pressure. But again, if you want to kind of deal with reverse osmosis, you could apply a pressure greater than that. And as you can see, it'll push all the water molecules back the other way, kind of pure water on this side, all the sort of salt and other stuff that you probably wouldn't want in your water gets trapped on the other side of sort of the membrane or the filter. And again, that's sort of the process there of reverse osmosis. Now, there's a few different ways we could describe solutions as either being isotonic, hypotonic, or hypertonic. And let's talk about what those solutions are. Isotonic solutions are solutions that exert the same osmotic pressure as body fluids. Most IV solutions are that. And when we talk about isotonic solutions, there's really two solutions that we talk about as being isotonic, and that is something that's 0.9% mass to volume sodium chloride, or saline solution, or 5% glucose. So these are what are referred to as being isotonic solutions. And in an isotonic solution, what that means is you have equal osmotic pressure inside and outside of the membrane, if you will. So very classic example is if we take a red blood cell and put it into an isotonic solution, what's going to happen with that red blood cell is because the osmotic pressure inside the cell and outside the cell acting as a membrane, it is equal to each other. You will have basically, I'll just draw it out here. You have equal flow of water out of the membrane and into the red blood cell. So it's perfectly fine and happy in that type of solution, which is why IV solutions are isotonic. So when they give it to you, your cells don't go crazy. You know, they don't burst because of the difference in osmotic pressure. Now, when we have a solution that's hypotonic, hypo means less than, right? What happens is if we take that same red blood cell and we put it into that hypotonic solution, that means outside of the cell is less concentrated than inside the cell. So the cell is more concentrated. So by osmosis, what's going to happen is everybody from the solution is going to start to rush into the cell. And that's going to cause the cell to start to swell and burst, which is probably not a good thing, I'm assuming. And hemolysis will occur. So again, it's going to kind of rush everything into the cell, cause it to swell. A hypertonic solution means more than, which means the solution is more concentrated. So if we take our classic example there of our red blood cell, we put it into a hypertonic solution, what's going to happen now is outside the cell is actually more concentrated than inside the cell. So the cell is going to go, oh, I need to dilute this down. So all the water from the cell is going to run out of the cell into the solution in an effort to basically try to dilute it. It's going to cause the solution to shrink, and that's the process known as crenation, which is not a good thing. So we can use these as sort of a baseline as to whether or not the solution will be hypotonic, hypertonic, or crenation or hemolysis will occur. So for example here, if we took a red blood cell and we put it into a 10% glucose solution, we put it into a 2% sodium chloride solution, if we put it into a 0.9% sodium chloride solution, and if we put it into water, why don't you take, I know we're a little over, we're almost done, so we're just going to finish it here. Take a second or two and think about each of these. Think about what will happen to the red blood cell if we put it into each of these solutions here. And while you're at it, we'll add, we'll do 3% glucose as well. Okay, so let's talk about this real quick. So to help you decide that, that is where those numbers we saw earlier, the 0.9% sodium chloride, our saline solution, our 5% glucose. Again, remember that these are isotonic, which means those are the ones really you want to use to kind of determine what's going to happen here. So if I slap that red blood cell into a 10% glucose, 10% is greater than 5%, which means that this solution here is a hypertonic solution, right? So this is a hypertonic. And in a hypotonic solution, that means outside the cell is more concentrated than inside the cell. And this process right here in the center is going to happen. Basically, the cell is going to drop out all of its water to try to dilute the outside, and it will go through crenation here and start to shrink. Now, when we put that red blood cell into a 2% sodium chloride, 0.9% is isotonic, so 2% is higher than 0.9. So this also will be a hypertonic solution. Also means that the cell is going to lose all of its water and try to dilute the outside and go through crenation and shrink. Now, if we put it in a 0.9% sodium chloride, as we can see, 0.9% sodium chloride is isotonic, which means the cell will have equal amounts of water going in and out, and nothing bad will happen to it. It will be very, very happy, and it's an isotonic solution. If we look at 3% glucose, 3% glucose is less than 5%. So less than means that this is a hypotonic solution, which means this is the situation right here. The water from outside is less concentrated than the inside the cell, so the water is going to rush into the cell, going to cause it to swell and burst, which is known as hemolysis, right? And lastly here, water. And you may think water, not a bad situation, right? Water's all right. But water has no osmotic pressure, which means this is actually a hypotonic solution, which means it's actually less concentrated outside than inside the cell. And actually our second guy here is what's going to happen. All of the water is going to run out of the cell and go through crenation here. I'm sorry, go through, yes, crenation and shrink. So that obviously would not be a good situation there. That's, I feel like I wrote something backwards here. I'm sorry, it's gonna, not crenation. That's a hypotonic. It's going to do the same thing as this guy here. I'll write the right thing there. It's going to swell and go through hemolysis, right? There we go. That's a little bit better. So it's a hypotonic. Water is going to come in, going to cause it to swell. So it's actually going to be this guy here. My bad. Like that did not seem right, what I was saying there. So again, hypotonic, water is going to rush into the cell, cause it to swell, and then cause it to burst, which is hemolysis. So important for this type of questions, obviously, is to know these guys here, what is considered an isotonic solution. And although we oftentimes talk about in terms of sodium chloride or a saline solution, it doesn't always have to be sodium chloride. It could be something, other type of ionic compound, potassium chloride, something like that. But most of the time people talk about it in terms of sodium chloride. Any questions on that there? All right. And lastly, just to finish up, dialysis is a process similar to osmosis. It allows certain size molecules basically to pass through, and other size, which again are a little bit large, to not pass through. And a dialysis bag such as this can be used in a laboratory. Again, you can't really see it, but there's little holes in it, again, that allows certain size molecules to pass through and other size molecules not to pass through. Obviously in our body, our kidneys, right, sort of work like that. They sort of filter out certain size molecules, waste products, and stuff like that, and allow other ones obviously to pass through and stuff like that. So that's sort of again why people that have sometimes kidney issues need to get dialysis because of that. They don't have that sort of natural, I'll call it filtering process, I guess, to allow certain molecules to sort of be filtered out and pass through and stuff like that. And that should wrap chapter 10 here. Any questions on that? All right, so a couple of reminders. Again, the exam has been moved to Monday to give you some extra time, so you're not learning it today, I guess, and testing on it tomorrow. It will again cover all of chapter 10, all of chapter 9, and again, that small little section of the gas chapter that you weren't tested on, which I think basically covered real gases, root mean square, and diffusion type issues, which is not too much out of that chapter. And then obviously these two chapters. So like I said before, tomorrow will be just a normal day. We'll lecture. We have, I think, the colligative properties lab tomorrow, which will be good review because again, that will be on your exam on Monday. So that will also give you an opportunity to kind of work through those problems as well tomorrow, which will help you out hopefully for the exam that's coming up. Let's see here. Today we are starting a next experiment, which is experiment 12, I think we might be on. Or yeah, I think it's 12. And it's another gas law experiment, so not too bad. So we'll talk about that like we've been doing, and then you could watch the video. So since we ran a little bit long here, why don't we start at 10 o'clock? Give everybody a chance to get up and stretch and everything like that. So we'll start lab at 10. We'll talk about experiment 12, which I think should be, and again, another gas law type of experiment and what you need to do for that experiment. And then I think that would be it. Any other questions on any of that stuff? Again, if you didn't put here, make sure you do put here. And again, we'll start lab since we went a little bit over here at 10 o'clock today. Okay. I'll see everybody at 10.